Thanks for the introduction, Graham, and welcome everyone. We split this talk into two parts. In the first part, I'll talk about the science that informed the physiographic zones. And in the second part, Lisa will then talk about the physiographic zones, about their characteristics and water quality outcomes. So the science part was really all about understanding the drivers of water composition. And one of the key questions we wanted to answer was, why do we see different water quality under the same land use? To answer this question, we looked at a whole lot of groundwater, surface water, soil water samples, in total 28,000 samples. And we focused on the shallow environment, so surface waters and shallow groundwater. So everything that is connected to surface processes. We didn't really look at the deeper groundwater that is basically disconnected to the surface processes, because it takes centuries to millennia to actually reach those deeper layers. What's really the fundamentals of the science part was that water composition contains information on the sources and the pathways the water has undergone. So for example, redox indicators. These include dissolved oxygen, nitrate, iron, manganese, major ions, which include things like potassium, calcium chloride, and a whole lot of other parameters and metrics. So not just water quality, but really was all about water composition. The whole set contains information on things such as whether the water has undergone any redox reactions, so denitrification, the pathway it undertook, its recharge mechanism, etc. And all of these sources and pathways are actually driven by a landscape or your setting. That might include soil permeability or topography. So these are the things we actually have maps for. So if you then link those landscapes with the processes and sources, you can actually map these sources and processes. And with that, you can infer the composition of water or water quality at any point spatially at any point. And that's exactly what the physiographics project was about, by trying to link the landscape setting with the processes and sources. And we used the hydrochemistry to inform us how to do that. So to map these, we call them landscape attributes. So these are our mappable units such as topography or soil drainage. That determine water quality. We summarize these sources and the processes that I've talked on the slide earlier into 4 key processes, which are atmospheric. That's basically determining your composition of your precipitation. That's driven by topography and distance to the coast. So you can imagine rain falling at the coast will have a higher salt content to rain falling inland or at higher altitude. The second process is the weathering process. It determines mainly the major ions that end up in the water. That is dependent on your rock type or your composition of the rock and how old it is or how weathered it is. So you can imagine if you put a really fresh limestone piece in water, it will leach a lot more ions into the water compared to if you put a grey rocky, really weathered gravel pebble into water. The other 2 processes, are the hydrological process that determines the source and the pathway the water undertook, and the redox process determines whether denitrification occurred or not. And these 2 are very important for water quality outcomes. So if you know those 2, or you can map them, you can infer water quality at any point in space. If you look at all 4 of them, you can estimate water composition at any point in space. And in the next few slides, I'll focus on those water quality ones. So first up is the hydrological process attribute layer, or short HPAL, which, as I said before, determines the pathway or maps the pathway and the source the water undertakes. So imagine in a lowland setting, the water doesn't travel very far to actually reach surface waters and groundwaters, compared to an alpine setting where the water actually travels quite far to reach lowland groundwater systems. So here you have your 2 examples of your sources, lowland and alpine. The water then also travels through smaller scale pathways. This could include in an alpine setting where you have quite steep terrain, you have overland flow or lots of lateral flow. In the lowland setting, you have more deeper drainage. You have your artificial drainage or even open soil cracks where the water just gets into the subsurface. These are very important for water quality outcome. Imagine water traveling through deep drainage will go a lot slower through the subsurface, have a lot more time to interact, so the contaminants can be removed through that process compared to water traveling through open soil cracks. To map the hydrological process layer, just as an example here, we're showing the gradient in subsurface drainage and permeability. So you have, on the one end of your spectrum, you have your hard rock where you don't really get any permeability except into the subsurface, except if you have cracks. So you get a lot of overland flow or lateral flow. It's very different to your coarse gravels, which have a high permeability, so you get a lot of deep drainage. Other end of the spectrum, your clays are less permeable, so you get less deep drainage, but a lot of lateral flow. You can see that it seems like there are sharp boundaries here, but they're actually not. You could have lenses of clay in your coarse gravel material. So actually, we set those boundaries by looking at the water quality and produced these maps. On the left-hand side, you can see the water source map. So as I mentioned before, the alpine is one of the sources. So all that light blue over in Fjordland. These areas, so that's where you get a lot of overland flow and lateral drainage, very steep terrain, compared to the lowland yellow setting, where you get a lot more deeper drainage mechanisms. On the right-hand side, we're showing the source of the surface waters. Just as an example, the dark blue are all the rivers that originate in alpine areas. And we can also produce a lot more finer scale maps that become really important for water quality, such as deep drainage or overland flow, and Lisa's going to talk about that in a minute. Now the redox process attribute layer, or short RPAL, which is, as I mentioned before, determines whether denitrification occurs or not. It also determines the mobility of phosphorus and the solubility of iron and manganese. It is mainly dependent on your permeability of the soil, so how quickly the water moves through and whether there's enough time for the microbes to do denitrification, and the organic matter content in the subsurface, which we also refer to as electron donor content. And here again, we're showing the gradient. On the left-hand side, you really have your mineral subsurface, where you don't really have a lot of organic matter in there, actually close to none. And the water moves really quickly through, so you don't really get any denitrification under this setting, compared to your organic subsurface, where the water moves really slowly and you have a lot of organic material supporting denitrification. Again, there's no sharp boundaries. Where can you say the denitrification potential is high or low? So again, we used hydrochemistry or water quality to actually inform us where those boundaries should sit in terms of water quality outcomes. And we produced the following map in really red, showing the high soil denitrification potential over high geological or subsurface denitrification potential, and in blue, low soil denitrification potential over low geological denitrification potential, and a lot of other colors just showing the different categories in between. So if you then put those two layers, the hydrological and the redox layers together, you can infer water quality outcomes. And that's just showing the concept of it. Imagine you have your hard rock setting where you have a lot of overland flow, nothing really drains into it. It's quite mineralized, so you don't really get any denitrification. So you can get a water quality outcome called A1, let's assume. Under the lowland setting, where you get a lot more deep drainage, it depends on what material you have, or if you have a lot of organics in your subsurface or not, whether denitrification can occur. So you can get a whole lot of other ranges of water quality outcomes. Again, no sharp boundaries. I mean, where do we set those boundaries? and you can use water quality or water composition to help you set those boundaries. And to be a bit more, give a better example here, you can use cluster analysis, for example, that lumps all the water samples together that have a similar composition. Then look at what composition they have, and that tells you where you can put those boundaries. Thanks.
Thanks, Monique. So what we get from that is land areas with similar combinations of biogeochemical and hydrological controls result, unsurprisingly, in similar water quality outcomes. So that means we can then create a tool to help people with their land management. What we know about the setting can help inform then what people need to do in terms of mitigation and advice that we can provide. So Southland has 9 physiographic zones. There's variants that exist within these zones for different finer scale pathways, and these are focused mostly on overland flow and artificial drainage. But there's also a lot of variation within the unit, and that just occurs naturally, but when you're looking at the collective of water that comes out of an area, the overall chemistry presides. We think of the water as the source of truth. Yes, you might have finer scale mapping soils and things like that, but overall it's that collective of the unit, what's happening in that land area. So physiographics have been delineated using the science that we learnt from the water chemist composition, as well as a lot of expert opinion and knowledge. It really sits on a lot of the underlying maps that already exist in New Zealand. For example, Topoclimate South Soil Series, SMAP, NZARM, QMAP for your geology. So those what we use to form our map boundaries. But it's really the water composition that informs what the unit is. So these zones have been created for policy application, and they're really a generalised setting. But they can help us answer 2 key questions. Firstly, how do contaminants move through the landscape? So is it overland flow, artificial drainage? Is it laterally in your bedrock? Or is it your deep drainage or leaching? And what natural processes influence the contaminant concentrations as the loads move through the landscape? So they're kind of like a bit of like a cheat sheet. What's happening in the environment? What do I need to know and what do I need to focus on? So I'm going to go through each of the zones and give you a bit of a rundown of each of their key characteristics. So the first zone is the bedrock hill country. Firstly, I'm actually going to say I'm just going to focus on the 8 agricultural zones rather than including alpine. But the key features of this bedrock zone is that it's got shallow soils overlying bedrock. It's in a high rainfall area, and there's also a limited groundwater resource. But given that, deep drainage is actually still the main pathway, but water just moves laterally along the contact with the bedrock. Because of that, it has a high denitrification potential because the soils are high in organic matter and they can reduce any nitrogen in these areas. So therefore the contaminant load that it carries is very low, and also there's a high amount of precipitation in this area, in these settings. The receiving environments are typically surface waterways from the zone and other physiographic units. There is variance within this unit for both overland flow and artificial drainage, and that just means at different times of the year when the soils are very wet, deep drainage is no longer the key pathway, but things like overland flow or drainage become the dominant pathways. And when we know about the dominant pathways, we can then think about how contaminants move. For example, nitrogen is predominantly leached, so we know anything when we have deep drainage, nitrogen becomes a key issue. In overland flow and artificial drainage, all contaminants become an issue because you're bypassing the mechanism for your soils and your aquifers to remove and attenuate, filter and absorb contaminants. So here, actually, and every time we have an overland flow and artificial drainage variant, all contaminants are a key issue. From the bedrock hill country, we get down onto the flatter parts of Southland. And oxidising zone is where you find intermediate aged alluvial terraces. They're predominantly well-drained areas, fine to coarse textured soils. The recharge here comes all from local precipitation, and the water infiltrates through the soil matrix. So deep drainage to groundwater is the main contaminant pathway. These areas have a low denitrification potential. So there is a risk to your groundwater of nitrogen building up, and this is where we see some of our nitrogen hotspots occurring in Southland. This unit also has variants for overland flow and artificial drainage. Old Matara is a unit that's found only in the Matara catchment, and this is its name. It's also the oldest landform in Southland. So it's formed on the Luggett Shotover Formation, so it's a very highly weathered aquifer with clay soils, so very, very low denitrification potential, and we do get our highest concentrations of groundwater located under this unit. The opposite to the Old Matara is the riverine. So here we're on very young alluvial terraces, but they're hydrologically connected to the alpine and hill country settings. So there's a lot of flushing, high dilution potential in the zone. That means you can be doing exactly the same activity as you're doing on your oxidising or your Old Matara, but you just don't see any accumulation of nitrate in the underlying groundwaters. This unit does, though, however, because it's essentially our transport to the estuaries, it can carry a high load of contaminants. It also receives a lot of drainage from the other units. And you can trace this unit from the alpine settings right down to the coasts along the main stem rivers. The next unit is glade. So this is kind of the opposite of our oxidising unit. Here we're getting into fine textured soils, and actually this is most of lowland Southland setting here, is the fine textured soils, imperfectly to poorly drained. This is identified by soils with redoxymorphic features such as mottling and glaying. And the key pathway is really through that artificial drainage network. So anything that we're going to do to improve water quality has to target how we're draining the land. There's low nitrogen in the deep drainage because of the higher reduction potential in the soils and underlying aquifers. Central Plains, again, given its name, it's only found in the Central Plains of Southland. It's the purple unit in the middle. And this one's a bit special. It's similar to the glade unit, so all those, what you just learnt from the previous slide still applies. But where it differs is in the soil characteristics. Especially, the soils here have been, clay-rich soils are derived from a mafic parent material, which means that when they dry, they're more susceptible to cracking. And cracking allows contaminants to rapidly bypass the soil zone. So in winter it behaves or when it's very wet, like a glade soil. In summer, highly stylised, you get these cracks forming. And what we see in the hydrograph is a near instantaneous recharge of the aquifer below. This unit is where we find most of the groundwater or compliance issues with green streams can occur in this unit because people, yes, are doing their best practice, but have not. But because of the condition of the soil, there's just a direct transport into either the tile drains that exist or straight down into the aquifer. The next unit is a peat wetlands. So here we've gone. The other units have been more about mineral aquifers and soils, whereas here we're getting now into an organic unit. So it has a very, very high denitrification potential. So you've got poorly drained peaty soils with high denitrification potential, but because of the redox condition of this unit, we've now moved into where phosphorus becomes soluble. So we have a P leaching issue under this unit. There's also a lot of variation in this unit because of the thickness of the peat, but it's typically highly drained, so highly modified with artificial drainage, and the main water quality risk in this setting is phosphorus and microbes. And the last unit I'm going to talk about is the lignite marine terraces, and this unit could be similar to the oxidizing or glade unit for the soils, but really what's underneath is what's important. Kind of think of below the root zone or in the aquifer. Here you've got lignite material, which is high denitrification potential, or a marine terrace, which have the same effect. They denitrify. So even though we would have thought that nitrogen will be an issue under this unit, we don't accumulate any nitrogen hotspots, and it's a much safer area to do some of those high intensity land use activities. So what we get from all that is a water quality risk assessment that can identify your key pathway and the contaminants, and then the water quality risk associated with that. But all this is actually independent of land use. So then this is now when you need to bring in your land use activity and think of it now in this context. So this project has a massive list of acknowledgements. It was led out of Environment Southland, but a large number of people contributed to expert knowledge, to reviewing and producing the lovely figures that you see in this slide. So thank you. There's information sheets on each of the zones at the back of the room if anyone would like to take some.
Thank you.